blindfolded taster sits before a bowl of the restaurant's legendary secret sauce. She's determined to reverse engineer the recipe, identify every ingredient and its amount from taste alone. But before her first sip, a mathematician at the table asks a crucial question. Is it even theoretically possible to identify each ingredient from taste? Some ingredients might be indistinguishable in combination. Answering this question first, before any tasting, can save hours of futile guessing. The sauce has 7 ingredients. These are the parameters of your model. You can only taste the final product. These are the observable outputs. The question isn't about your palate's sensitivity or the number of tastings. It's structural. Given the recipe, the mathematical form of how ingredients combine, does each ingredient uniquely affect the taste? If 2 different amounts of an ingredient produce identical tastes, no amount of tasting can distinguish them. Salt is straightforward. Half a teaspoon of salt produces a mildly savory taste. 1 teaspoon produces a noticeably saltier taste. 2 teaspoons, too salty. Every distinct salt amount produces a distinguishably different taste experience. The mapping from salt amount to taste contribution is 1-to-1. Salt is structurally identifiable. Its value can, in principle, be uniquely determined from the output. Now consider 2 herbs, oregano and marjoram, that combine synergistically. 2 teaspoons of oregano plus 1 teaspoon of marjoram produces exactly the same flavor profile as 1 teaspoon of oregano plus 2 teaspoons of marjoram. The herbs interact in a way that their individual contributions are inseparable. Infinitely many combinations of oregano and marjoram produce identical tastes. You can determine their sum, but not their individual amounts. They are structurally non-identifiable as a pair. SIAN, Structural Identifiability Analyzer, performs this check mathematically. Given the ODE system defining your model, SIAN uses differential algebra to test each parameter. It generates the input-output equations and checks whether each parameter appears uniquely. The result is a report card. Each parameter is classified as globally identifiable, locally identifiable, or non-identifiable. This analysis is performed symbolically, without any data. It's a property of the model structure. DAISY differential algebra for identifiability of systems takes a complementary approach. It derives the input-output relationships more directly and checks if the parameter-to-output mapping is injective. DAISY is often faster for large models, but may miss some edge cases that SIAN catches. Together, SIAN and DAISY cover most identifiability questions for ODE-based models. Your glaucoma QSP model with 14 variables was analysed with both. 10 of 13 parameters were identifiable. 3 were flagged as non-identifiable. Check identifiability before parameter estimation. Always. If a parameter is non-identifiable, no algorithm, no matter how sophisticated, can determine its true value from the available outputs. SIAN takes minutes. Failed parameter estimation campaign takes weeks. The mathematical check saves experimental and computational resources. And it prevents the most dangerous outcome, a parameter estimation that converges confidently to a meaningless answer.